Tuesday, we gave you a relationship between, another relationship between electricity and magnetism. We said that because a wire that carries an electric current generates a magnetic field, if that wire was exposed to an external magnetic field like this, we'll say these black lines represent the magnetic field, then the two magnetic fields, the one that was produced by the wire and the one that was external to that, the black one, would interact with each other to cause a force on the wire. We learned to describe the magnitude of that force using the equation F is equal to ILB, and we learned to describe the direction of that force using the hand rule for deflection, which remember said thumb in the direction of the electric current, which is to the right here, fingers stretched out in the direction of the magnetic field, which is down the page. The magnetic force in this case would be out of the page. Today what I want to talk about is not so much wires in magnetic fields, but individual moving charges in magnetic fields. So let's draw something similar to what we have right there, looked at on Tuesday. Let's make this my magnetic field, but instead of having a wire moving, or a wire that carries a current perpendicular to that field, say we have a single electron moving perpendicular to that magnetic field. We will once again describe the direction of the force on that particle by using the hand rule for deflection. And it's going to work exactly the same way as the hand rule for deflection on a wire. Thumb in the direction of the particle, fingers field, palm points. In this case, it would be out of the page. I mean, let's think about that. What did we do the other day? We studied the motion of a whole bunch of electrons going through a wire in a magnetic field. What are we doing today? We're studying the motion of one electron moving through the air in a magnetic field. There's not going to be any difference in the direction of the force. We still have electrons moving through a magnetic field. The force is going to be found in exactly the same way by that hand rule for deflection. There is a different equation, though. I'm not going to tell you what it is yet. But there is a new equation that's a little bit different than the one that we saw on Tuesday that describes the magnitude of the force. The direction of the force, exactly the same thing. The magnitude of the force has got to be dependent on, not on the current and the length of wire, but rather it's got to be dependent on other factors, properties of the individual electron as opposed to properties of the wire itself. All right, let's formalize this a little bit. There is a force. It is found by the hand rule for deflection. We will stick our thumb in the direction of the moving charge. On Tuesday, when we had almost the same page in your notes, we said the direction of your thumb would point in the direction of the current, which is really just the direction of the moving charge. Your straightened fingers would point in the direction of the external magnetic field. Now remember, there is two magnetic fields here. There's the one that's caused by the moving charge, but there's also the one that was already there, the external magnetic field. If we wanted to use the wire grasp rule, our bent fingers would point in the direction of the field caused by the moving charge. But the hand rule for deflection, our fingers point in the direction of the external magnetic field. Your palm will automatically point in the direction of the magnetic force. So if you have that situation where the electron is moving to the right through a magnetic field that's pointing towards the bottom of the page, we would stick our thumb to the right, our fingers toward the bottom of the page, and our palm, in this case, would point out of the page. We'll deal with the magnitude of the force soon. Right now, let's take a few minutes and work on part of worksheet number 11 that's going to provide us with a little bit of practice on the hand rule for deflection. See which way the magnetic force points, okay? A couple things that I'll remind you of. Number one, left hand rule for deflection if you're going to use a negative particle, right hand rule if it's a positive particle. Remember what happens as well if the particle is moving perpendicular to the field versus parallel to the field. I'm not going to tell you. Okay, I'm just going to ask you to just keep that in the back of your mind. If it's perpendicular, what do you do? Versus if it's parallel to the field, what do you do? Okay, so I want you to work on worksheet number 11, questions number 1 to 8 for now. Those should go fairly quickly. We'll give you some answers for those probably in about 10 minutes, and we'll go over a couple of those questions, and then we'll move on. Let's have a look at number 4. It says an alpha particle. Right away, we start thinking alpha particle, that's a positive particle. That's going to be a right-hand rule, right? Just draw attention to it so don't forget. Travels to the north. We say geographic north. Geographic north, which is really magnetic south. It's that way towards what we think of as the North Pole, but it really is the South Pole. There's a magnetic field that's pointing to the west, which is this way. Okay, that's west. Okay, that's geographic north. Okay, geographic east and geographic south. Which way does the magnetic force point? Well, let's stick my right thumb to the geographic north or magnetic south. Magnetic field points to the west. Magnetic field points to the west, which is this way. That means the magnetic force is going to point which way? We're going to say up. Now remember our frame of reference. In question number 3, the frame of reference is the page. So our answer is going to be expressed relative to the page. Toward the top of the page, bottom of the page, right side of the page, left side of the page. In number 4, our frame of reference is the Earth. So we don't have to do that now. In number 4, we can just say it's up. You could say up away from the Earth, but like that would be assumed if you say up, right? Okay, if it's relative to the page, okay, say that. But if it's relative to the Earth, just say up, down, left, right, whatever. Yeah, you could say that. Yeah, I mean, it's kind of an odd way of saying it, but that would work. Yeah. No, it's definitely not up on the page in number 4.
So it's not like north, it's out.
Well, it's not out of the page. Like if you're going to do it with north, south, east, and west, the Earth is your frame of reference.
So you got to use like up and down.
So you got to use up and down. Yeah. Number 6, an alpha particle travels out of the page to a magnetic field that points into the page. Once again, it's an alpha particle. If I have to use a hand rule, it's a right-hand rule. Traveling out of the page, so a magnetic field that points into the page. What do we know about that particle versus the magnetic field? They're parallel, which means the force is what? There is no force, right? The force is 0. If the field is parallel to the force, if the field is parallel to the motion of the particle, the force is 0. If the field is perpendicular, the force is found by the hand rule for deflection. And if it's somewhere in between parallel or perpendicular, then we don't know how to do it, and you won't know how to do it. All right? Good? Let's just take a quick little diversion again, just for a second before we take a look at questions 7 and 8. I got a map of Canada up here right now to illustrate something with direction. We've done a couple questions now where, like one of those, the question number 4 was, I think, on that worksheet that said, I think the particle was moving towards geographic north, and the field was towards the west. We can see in this room, not so much today because it's overcast with the snow, but usually we can see the mountains out the window. We know that's west when we look out the window, right? And we know, like intuitively, because we can see the road, those cars are traveling towards Calgary, so that must be towards geographic north. But what if you happen to be in an exam room like the cafeteria or the gym where you can't see out, and you're having a tough time kind of figuring out what's north, south, east, west? How do we do a question like that then? Here's what I want you to do. Make it up. Like, make it up. Seriously. Completely make it up. You just have to be consistent. Okay, we know that if we'll call this north, but remember it's really magnetic south, right? Geographic north. This is south. And we know that British Columbia is in the west. Geographic, magnetic, whatever you want to call it, it's west. And Nova Scotia is to the east. If you find yourself kind of turned around in a room with no windows, and you're like, oh man, like north, which way is north? Which way is west? It doesn't matter as long as whatever direction you make, geographic south or magnetic north, east is 90 degrees clockwise, and west is 90 degrees counterclockwise. Okay, let's say I was in that room, I couldn't see out, and I'm like, I don't know which way is north, and I make that way north. Okay, it's not. But if I make that way north and that way west, it's all good, right? It doesn't matter. It's all going to work out as long as you're consistent. So as long as you remember that it goes make geographic north, east, south, west, and then back again to north, it's all good. Even if north is wrong, as long as the rest of them are consistently wrong, consistent with that. Make sense? Okay, Go back to question number 7 and 8, finish those off, and then we'll take a look at one or both of those in about 2 minutes. Number 7 says, an electron traveling to the east experiences a force towards geographic north or magnetic south. We want to find the direction of the magnetic field. This is kind of using that hand rule for deflection, but rearranging it, right? Doing it in the opposite direction. Instead of saying thumb, direction of the particle, fingers, field, which way does my palm point? I'm going to say in this case, thumb points in the direction of the particle, palm points in the direction of the force. Let's see which way my fingers automatically point. So we got an electron traveling to the east. That's this way. Okay, particle going to the east. Okay, we've got a magnetic force to the north. That's this way. My magnetic field is going to point up, right? And we're going to say just up. We're not going to say out of the page because our frame of reference is not the page. Now, let's assume that you can't see out that window. Okay? And I'm going to turn around and face the same way as you guys are facing now. I don't know which way is north. I don't know which way is south. I can't see out the window. Kind of turned around here. So let's assume that that is geographic north. Well, if that's geographic north, then that is going to be geographic, that's going to be east, right? Which means that if I stick my thumb to the north, and I'm going to stick my, where are we here? My thumb to the east and my palm to the north, that means my fingers are going to automatically point which way? Up. Same as you did when I actually had the directions correct, right? It doesn't matter if you have those directions correct as long as you're consistent. Okay? Does that make sense? Yeah? Have a look at number 8 now. It says an alpha particle traveling into the page. Now we're back to the page as our frame of reference. Experiences a magnetic force to the right. Which way is the field? I like it when it's the page as a frame of reference because it's well defined. We don't have to visualize north, south, east, west. We got it right in front of us. My thumb is going to go into the page. My force is to the right. So thumb, palm to the right. My fingers are going to automatically point which way? Towards the top of the page. Towards the top of the page. Or you could say up the page, but your page is your frame of reference there. All right? If we want to find the magnitude of the force on a wire in an external magnetic field, remember it was this equation, F is equal to ILB. That is, if the wire was perpendicular to the magnetic field. If we want to find the magnitude of the force on an individual electron in a magnetic field, assuming that particle, that electron is moving perpendicular to the field, they would say that force is equal to Q times V times B. What does Q stand for? The charge. What does V stand for? It's a little v. Speed. Yeah, not the velocity, but just rather the speed. And B stands for the external magnetic field strength. And the units for that are going to be in Tesla. Now notice that little upside down T. This equation assumes that the charged particle is moving perpendicular to the field. If it's parallel, the force is 0, and there's no point in even using an equation. If it's something other than perpendicular or parallel, then we won't do it. If you did, ultimately, if you had an electric current in a wire going through a magnetic field, like we did on Tuesday, up here, technically, you could calculate the force on every single one of the individual electrons in that wire, add them up, and that would give you the force on the wire. It's just a lot easier when you've got the wire to use the one equation ILB. But understand, it's really the same thing. You've got 50 electrons, and QVB times 50 would give you the same value as ILB. Right? Finish copying that out, and we'll leave it there, and do an example with that tomorrow.